Hello, and welcome to today's EHS Today webinar, Calculating Safety Distances, Stop Time Measurement. And it's sponsored by PILS Automation Safety. I'm Dave Blanchard. I'm the editor-in-chief of EHS Today, and I'll be the moderator for today's webinar. Before we begin, let me explain how you can participate in today's presentation. Okay, first of all, if at any time you're having audio difficulties or maybe the slides aren't advancing, something else is not working right, simply hit your F5 key to refresh your webcast console. If you're running pop-up blocking software, please note you will need to disable it to view this webinar. If you have any technical difficulties during today's session, please press the question mark help button. You'll see that in the upper right corner to receive assistance in solving common issues. The webinar technology that we're using will
Dave appears to have disappeared.
Can I be heard? Hello?
Thomas, I can hear you.
Yes,
Okay.
Thomas, we can hear you.
Because I had a message on my screen with an with a triangle, with a warning triangle to refresh.
Okay, you're back, and Dave will probably be back on. Everybody, Dave, our moderator, will be with us shortly.
Okay.
Let's see. Let's give him another minute. I can see he's come back on. Dave, are you with us? Give him another minute, and then I will. I think I'll launch into the rest of the script for us, okay? This webinar technology allows you to resize the presentation by clicking the maximize icon in the upper right corner to enlarge the window. We welcome your questions during today's event. To submit your questions, simply type your question into the Ask a Question window on the left side of your screen, and then hit the Submit button. We'll be answering as many questions as possible during the Q&A that will follow the main presentation, but please feel free to send in your questions at any time, and we'll add them to the queue. Be sure to check the Resources tab on your console for resources provided by our sponsor, PILS Automation Safety. Please also be aware that today's session is being recorded and will be available on the EHS Today website within the next day for you to review. You'll be notified by email when the archive is available. When the webinar ends, please take a moment to complete the feedback form that will appear on your screen. Now, let me introduce our speaker. Thomas Hertig is the Technical Services Engineer with PILS Automation Safety LP. Thomas began his long career as an electrician apprentice and moved on to get his master electrician degree in 1991 and his electrical engineer degree in 1993. Thomas has worked at PILS Automation Safety for the past 24 years in various positions, including sales, safety consultant, technical trainer, and now as a technical services engineer. For more about Thomas, check out the Speaker Details tab on your console. With that, welcome, Thomas. The floor is yours.
Thank you so much, Susan, for the introduction, and welcome to today's webinar, a presentation of calculating safe distance, stop time measurement. So we will be looking at presence sensing devices, PSDs, and interlock guards, and how they relate to the safe distance measurements and the machine stop time. The objective today of this presentation is we will talk about some aspects of the risk assessment, concept of presence sensing device safe distance measurements, the introduction of presence sensing device installation requirements, and also one of the methods of measuring machine stop time to validate an installation. Also, we're looking at assessing interlocked guards. And then we will have a section with conclusion and some references that may help you further for your design. Machine risk assessment. Machine risk assessment is in the aspect of machinery safety, as I call it, the most important assessment that there is, because all additional results and also all uncovered information are being documented in the risk assessment, and it's a very good document to basically go back on and reevaluate. So a risk assessment is a process that is documented. It's a physical examination and inspection of a machine or process or piece of work equipment that is carried out under the guidelines of national and international standards. So, for example, you find risk assessment standard in an international standard ISO 12100 or in the ANSI standard domestically B11.0. And again, the purpose of the risk assessment is to identify hazards associated with the equipment. You estimate the risk, you evaluate the risk. And of course, more importantly, after is you determine the risk reduction that may be applied to reduce the risk in accordance with applicable legislation, standards, and best industry practices. And also risk assessments, they must be dynamic. So if your work equipment, the machine, or the work itself changes, the risk need to be reassessed. Now, if your risk assessment would call out for a presence sensing device after you look at possible risk reduction, then the following presence sensing devices are available. And here is some of the examples about presence sensing devices. There are safety light curtains, safety area scanners, two-hand controls, safety mats, interlock guards with guard locking, also future new technology that is on the market. And here in the picture you see a type of machine where you have a person, standing on a mat, an interlock guard, two-hand controls, light curtains, and here on the bottom you see a scanning area of a safety scanner. Distance, because they protect the operator from reaching the hazard, and reach, distance, and also time is involved. So we have to look at the following. We have to look at the machine stop performance. So in order to effectively implement and use these presence sensing devices and interlock guards, the machine must exhibit the following stop performance characteristics. So no full revolution stops, so no cycle completion, no fluid power, circuits with valves continuing along hazardous motion to the end of the stroke. Also look at that the stop time is consistent, limited, and stable. And also on certain machines, the stop time can vary, also with the age of the machine and usage. And so you got to use the worst case. All this relates to a safe distance. So we have the basic formula that is derived from the ISO standard 13855. So the basic formula is S equals K times T plus C. S is the safe distance that we need to calculate, or that we need to want as a result, how far we need to be away from the hazard with our PSD device. K is the body part approach speed, T is the overall machine stop time, and C is the intrusion distance. A quick look at the approach speeds. Domestically for NCP 11.19, K, the operator approach speed, so K is 63 inches per second or 1600 millimeters per second. For ISO 13855, for that international standard, we have two speeds. We have the 2000 millimeter per second or 99 inch per second when we're at a distance between 100 millimeters and 500 millimeters away from the hazard, and that's the hand and arm speed. And when we are further away, more than 500 millimeters from our hazard, then we have an approach speed of 1,600 millimeter or 63 inches per second, and this is called the walking approach. Again, you got to look at your application, what speeds you need to choose based on distance and situations of the personnel or person approaching your machine. Coming to the overall machine stop time, well, we have several phases that we need to look at, different aspects. So here you see a diagram. It's the speed on the left over time. So we have at the very first on the left, we have our detection of the person by our presence sensing device. So that's the first contact, breaking a light curtain beam, stepping into an area scan or scan area, stepping on a safety mat. And now this red column here, now our presence sensing device has a response time. So this is our first time element we've got to look at. Now our presence sensing device sends signals to the control system in the control panel. So we have a machine control response time. This is in yellow. And then all this in blue is now the complete machine deceleration. And this can have, many elements, mechanical, hydraulic, pneumatic. So this takes quite a significant time to run down until we reach velocity of 0 speed, 0 millimeters per second. Okay. So here's a breakdown of the stopping time as we just seen at the previous slide. So we're looking at the machine stopping time. That was the whole area in blue of our diagram. Then we had the control circuit response time. This was the yellow portion, the yellow bar. And now this, can consist of multiple elements. So you have control components, safety modules, safety field bus systems, safety PLC. You have mechanical components. You have pneumatic, componentry system, hydraulic, and so on. So this plays all a role for the control circuit response time. Then, as we have seen also previously, we have the response time of our presence sensing device. And then we have, for example, over time, possibly the stop time deterioration over time for certain equipment that you need to take into account. That's why these measurements should be done frequently if there's a chance that you may have a time drift on specific equipment. Okay, now we're getting more and more in thoughts to the formulas and filling out all those variables that we need data for. So we have the approach distance. This is K times T is the distance a person will have traveled towards the hazard after detection and before the hazard has stopped. And that is based on the resolution of your presence sensing device, so beam spacing, resolution of an area scanner, and the like. The intrusion distance now C is the distance of a body part, usually the hand, that may move beyond the detection zone towards the hazard before the presence sensing device detects it. And C depends on the resolution or the sensitivity of our presence sensing device. So here you see the C, it's the possibility reaching between two beams or the spacing of two beams until we can be detected by our presence sensing device. So we have also formulas in NCP 1119, and we have also what's called a depth penetration that's similar to that factor C. Now we have here a table. This is an example for a vertical sensing field for presence sensing device. So for a light curtain, finger, hand, or body protection. On the left, you see the column there with the resolution. Then we have the calculation formula and some notes. So here you have the resolution. If the resolution D is smaller or equal 40 millimeters, then we have two choices for the approach speed, either the faster one, the 2000 millimeter per second, or the 1600 millimeter per second. Distance anticipated for your PSD device. So if you're between 100 and 500 millimeters, then you use the 2000 millimeters per second. If you're possibly further away, more than half a meter or 500 millimeters, then you use the walk approach speed, the 1600 millimeters, and the formulas you see below. If we're in a beam spacing that goes beyond 40 millimeters up to 70, then you see you have the approach speed of 1600 millimeters times the overall time, and then you have to add this 850 millimeters. Here is also some information about if you're using either a single beam, multiple beams, and the beam spacing and the heights of those beams. You can see that on the left. Okay, so that's the table for the vertical sensing field. Not only do we need to look at distance, but in some cases we even may need to be further away, because there might be a chance for a person still to reach over our presence sensing device, being able and possibly reach the closest hazard point of the machine. So if we have a fairly short type of light curtain, there might be a chance that you can reach over. And in the standard 13855, there is tables where you take the measurement of the highest beam for your protection device. That's a measurement B, and we will get into examples in the following slides. Then you have the height of the hazard zone. This is the A, and then you have a table, and where A and B crosses, you either, if there's a value, you either have to add an additional distance or you may not. So we will get into some examples later on. Validation of a presence sensing device installation. So we have two parts. We evaluate the installation and also the compliance with the installation requirements. A manufacturer of these presence sensing devices, they give you excellent information about the possible situations that are most common in regards of machines that are out there. So I always love looking at these operating manuals and seeing examples. It's great. Also then, make sure that the presence sensing device cannot be easily circumvented or tampered with. There are instances where, sometimes they could be manipulated with and they don't function correctly, which is definitely not a good thing. Also, when you calculated a safe distance, for example, on an existing machine, well, you do how to confirm that. You measure the actual stop time, calculate the distance, and compare with the actual. Of course, for a new machine, you will have the result of your calculations. Right. Now, there is a method that you could use. It's called the video camera method. So this is a more practical approach, very good for estimation and also for confirmation. But also, please have a look at the respective machinery C as in Charlie type standard for the machines, because those C standards, those ANSI standards or EN standards or international standards, they give you information on the specific type of machines and give you formulas and give you guidance on how to make this basically fit your application needs. So again, camera is one of the methods. So you can take a video of the machine during a stop event. So here you include a state of the safeguarding device initiating the stop signal. So with the video, you put it on a tripod, you can use a camera. In the view, you have your presence sensing device, for example, the light curtain, and you have the area where you can see the LEDs, the red and green, and you have a good view of your machine with all the motions. And you will take a video. So you analyze the event then frame by frame to calculate the stop time and take several videos so that you have a consistent stop time performance. So take at least 3 videos. Now, getting into more details. So the video method. So a standard movie clip, for example, is taken at 30 frames per second. 30 frames per second provide 33.3 time increments. After the typical walking speed, for example, is 1.6 or 1600 millimeters per second or 63 inches per second, this would give us a resolution of 53 millimeters per second. Of course, camera settings can vary, so you got to make sure that you know how many frames per second your video camera is recording the video. Smartphones, digital cameras, or digital camcorders are capable of making movie clips. Then use a tripod to have a very stable viewing of your machine video, and then after that you can use a video analysis software where you can definitely then count the frames. So the video are as follows. So you determine the hazard location, measure the current safe distance if applicable, determine the critical machine motion and highest speed, select the camera view, monitoring the LED on the light curtain, and then of course at the view of your machine, you video the stop event. So you initiate breaking a light curtain beam, you see the LEDs change on your video. Within the same view, you have the machine also then stopping after a elapsed time. That's why those frames per second come into play. Also, you need to look at the depth penetration based on your presence sensing device installation. That depends on your beam spacing. Then you calculate the required safe distance and compare it with the current one. Now we're getting into an example. Here it says exercise 1. Is this safe distance sufficient? So here's some given data. So we have a normal approach for that person walking towards a piece of equipment. We have the ESPE type 4. ESP stands for electrosensitive protection device. We have the height is 1,000 millimeters. We have a resolution of our PSD device of 14 millimeters. There was an overall time measured of 125 milliseconds. And the existing result as it is 1,000 millimeters. And now we want to make sure, is this sufficient? All right, so we take our data from before, look at normal approach. So we have the D, we're smaller, smaller than 40 millimeters because we're at 14. The height of the hazard zone is 1,000 millimeters. We have also the distance S because it's an existing one. The label says 1,000 millimeters, so we're greater than 500. The height of the detection zone is also 1,000 millimeters. So we use the formula S equals K times T, and then we have the 8 in the brackets there, 14 minus D in millimeters. So we fill in the blanks here. So it's our approach speed because we are further away than 500 millimeters. So we use the 1600 millimeters approach speed. We had the overall time measurement of 0.125 per second. And then we had the resolution of our PSD device is 14 millimeters. So this will become 0. So our result now is 200 millimeters. Well, that's very short, right? So is this distance sufficient or not? Well, we have 1,000, 200. So what we're going to do, right? So now we got to look at into a possibility of reach over. Right. And also 200 millimeters we cannot choose because it says here for a 1600 millimeter per second approach speed, you need to be at least 500 millimeters away, which we still are with the 1,000, but we still need to check because our height of our presence sensing device is 1,000 millimeters. And you will see on the next slide, it says that we gotta look at the height, and we need to make sure that we don't have a reach over situation. So it says here, protective structures less than 1,400 millimeters, 55 inches. And in our example here, we have 1,000, so we're lower. It says here, should not be used without any additional safeguarding measures. So because of the possibility of reach over and getting to the hazard without being detected by the presence sensing device. So here we have as number 3, the reference plane. We got our protection presence sensing device, the light curtains at a certain height. We have the height of our hazard point. Here's the height of the highest beam. So, and then overall here is, our S and this CRO. So RO for reach over, this might be a factor that we may have to add if we, go into this specific table. So we're looking at, we have per ISO 13855, there's a table 1. And here we have the measurement height of the hazard zone. That was 1,000. Height of the upper edge of our presence sensing device, that was 1,000. So we're looking at here, our light curtain, the upper edge, 1,000. We had the height of our PSD, of the hazard. And where these two meet, we have here a number. That's the 1,150 millimeters. That's our CRO. So based on our results, the 200 millimeters now, we need to add this 1,150. That makes it 1,350. And initially we had 1,000. So our distance was not sufficient. So what can be done in some cases, right? So how to address a problem? There might be some ideas, right? You can move the light curtains further back. the further back, then the reach, is it's not possible then if you keep further away. But real estate, is definitely, important. But also, you got to make sure that you cannot stand behind a light curtain, or that you can reach around a light curtain not being detected. So, light curtain to move back, limited use. You can slow down the movement of the hazard, because we know that time is very important. So if you have a faster stopping time, then certainly this has an impact on your safe distance. Also, you can say, okay, if a light curtain doesn't work, in this case, maybe I can use interlock guard, replace it with. All depends on how often you need to access or interact with a piece of equipment. And here now it says here, replace with a larger light curtain. Well, make that light curtain taller, right? So that's another aspect. But then again, always think about that it should not be possible that you can stand behind the light curtain not being detected, or, it's not good if you could reach around the light curtain from the left to the right. So additional guarding is required in those cases. Now we're looking into laser scanners, two-dimensional sensing field to detect persons. So here are some examples on installations. So you have laser scanners on close to the floor height, or laser scanner mounted at a certain height, or laser scanners mounted at an angle. So the formula, well, the generic formula is still S equals K times T plus C, but now the formula changes in here because of our type of sensing device that's also out of 13855. So here you have the 1200 millimeters minus 0.4 times the height. And you can calculate the height of your protection field. Height equals 15 times D, again, is the resolution for the sensing device, your scanner, minus 50 millimeters. Also here, the maximum height may be 1,000 millimeters. Again, you got to make sure you detect the person before that person can reach the hazard. Also, the system response time need to be considered when defining the time for a scanner, and the scanner itself, our present sensing device, has a time delay. So for example, 80 milliseconds, but you will see that specific data for the scanner from the specific manufacturer. Okay, now we're looking at exercise on a laser scanner. So it's an ESPE type 3. And we have the resolution of 70 millimeters. That's given. Then we calculated the height of 300 millimeters. That came from the formula 15 times bracket open D minus 50. D is 70. So if you have this, fill in with 70, the result is 300. The overrun time of the machine was measured with 180 milliseconds. So here, because we have from our AOPDDR device, our area scanner, and AOPDDR is active up to electronic protection device to diffuse reflection. So we have the machine rundown time and our time of the present sensing device. So now, here now again, as an existing result or calculation, we have 1,000 millimeters. All right, so now we're looking at and fill in some of the blanks and say here, okay. So we're looking at the formula that was the approach speed 1600 millimeters per second times the time plus this height with our resolution. So we fill in that. The height was 300 millimeters. And then here we have the 288 millimeters plus the 1080. We add those up, and we're looking at 1,368 millimeters per calculation. Initially, we had 1,000, so also that distance was not sufficient, as we see right there. Okay, so this was some aspects to scanners, but also what happens to interlocked guards. So here's a type of machinery. So if an authorized person, would open a guard interlock door, well, the interlock switch reacts, reaction time, system reaction time, machine run time. So that also applies. And that person, if it opens, should not, be able to reach the hazard zone and get injured. So we have also the aspect of time involved there. So we're looking at also out of NCP 1119 in that chapter I.9 or ISO 13855, we have also a safe distance, it's S or D. And then we have in brackets there K times T plus a D with the adder of GT. So we have the approach speed of 1600 millimeters per second, or maybe even faster. That depends on your risk assessment. It could be also the 2000. We have the 0.25 second stopping time for the hazardous motion to stop. And now comes that DGT that comes out of table E3 in the NCP 1119 standard. And that value, for example, here is 850 millimeters, because it is depending on the opening. If you have a round opening, if you have a slotted opening, a rectangle opening, and the respective finger, hand, arm, or legs, body parts that can enter the hazard zone. The measurement need to be taken at the nearest edge of the interlock guard. And here we have an example. When we put the formula into use here, we have 1600 millimeters times 0.25 seconds plus 850. So we need to be away at least 1250 millimeters. You will find also some information about interlocks in general in the ISO standard 14119 specific types. So what happens if you open an interlock door and the machine has a longer rundown time and there is a possibility of reaching the hazard? What can be done in these cases is you use an interlocked safety door switch with guard locking that would keep the door closed. And until your guard locking switch, and by 0 speed standstill will allow you the door to open. Here out of NCP 1119, we have 2 examples here. On the left, we have an interlocked guard, a sliding movable guard, like a sliding door. So here you see the person, machine hazard, and here you see the distances that are derived from the time measurement. And here is that factor DGT on what body part might enter the hazard zone. And here you have that specific opening. So that is for sliding movable guards. And the other example here is if you have a hinged, like a swing guard. So here's the angle, and then it opens up this way. And here you have the distance E, and you have the reach from this end. So again, if it is possible before that or before the system even stops that you can reach the hazard, then you need to look at an interlocked safety door switch with guard locking. Now we have some information in regards of some conclusions and references. So of course in this presentation, this is not a complete and exhaustive view. So got to look at the respective machinery standards, and I will get into some references a little later. So depending on your application or existing application, always consult the respective legal requirements and standards. Always look what's first legally required. Here in the United States, you would look at OSHA 29 CFR regulations. And if you find or need that it's not within in the OSHA book, then you can need to consult the respective ANSI standards, the type C, like Charlie standards for the respective machine type. Also, look at ISO and IEC standards or EN standards for specific machines. They are also called Type C standards. Then we have the ANSI standards and the specific machine type standards in ANSI, the Type C. For example, ANSI B11.2 for presses, hydraulic and pneumatic. That's a Type C standard. Or ANSI RIA 1508. Version from 2020, that's also a Type C standard. And also manufacturers of those presence sensing devices provide information on assistance for your design. Also, as a reference, some of the websites where to get these standards. So ISO standards is the International Organization for Standardization. They develop and publish international standards, and the website is iso.org. We have IEC, is the International Electrotechnical Commission, organization that prepares and publishes international standards for all electronic, electrical, and related technology. Their website is iec.ch. They're located in Switzerland. And we also have a reference to some websites in OSHA, so Occupational Health and Safety Administration, those OSHA regulations, 29 CFR, Code of Federal Regulations, or your specific state OSHA program. Of course, OSHA aims to ensure employee safety and health in the United States by working with employers and employees to create better work environments. And you have the website there, osha.gov. And then here, ANSI is the American National Standards Institute, and they oversee the creation, circulation of thousands of norms and guidelines that directly impact businesses in nearly every sector. And we have the website ansi.org. All right, and this would conclude now the presentation material. Thank you so much for listening in, and I would like to pass the baton back to Dave. Thank you so much.
Thank you so much, Thomas. Fantastic presentation. So
thank you.
Thank you, and we will now get to some questions. A few of you have already had a chance to submit your questions. If you have sat patiently and have not submitted a question yet, now is your chance. Just a quick reminder, at the very end of this webinar, you'll see a feedback form that will show up on your screen. Just take a couple brief moments to fill out that form, and that'll help us evaluate this webinar and determine your interest in future webinars. So let me start in with some of the questions. Thomas, first one is, it's a good question. Where can I get more information on the specific standards and regulations that I would need for my specific machinery?
Okay, so the first step is to identify the type of machinery. Could it be a press? Could it be packaging machines? Could it be a lathe? And do a search. For example, here domestically, you would look first in the OSHA, regulations. That's the legal aspect. And then you would look at the ANSI standard for the specific type of machine. So you can go and use the information from the presentation, go to the website, type in or do a search for the respective machinery and see if an existing, ANSI standard covered that machine. And that gives you guidance on how to approach safety, because those are the type C standards where industry professionals from manufacturing, from end users, from the legal point of view, from suppliers, they all work together on those standard committees, creating these standards. And those standards also help you with your risk assessment to identify all the common hazards related to this specific equipment. There is a risk assessment standard, and it gives you guidance, but specifically for a machine, you got to look at the specific existing type C standards, and that gives you excellent guidance for that.
Okay, thank you. We have a question about a specific type of machine. These questions will be about lapping machines. So the question is, can we install PSD for lapping machines? If yes, what type of PSD are recommended for lapping machines, and will it impact CE marking on the machine?
Oh, that is fairly complex, because now with, in general, of course, you need to guard your machine based on your risk assessment. Again, it falls back even if you build a machine domestically or international, or for the European Union in the machinery directive for the European Union, it shows that you need to do a risk assessment and a very detailed, of course. And you use now the EN standard for this lapping machine, if that exists, and follow that through. And if a safeguarding aspect like a risk reduction would call out for a presence sensing device, it is on the designer to define that type that is practical, that keeps the person away from the hazard. So, and that has impact domestically as it has impact for CE marking. So it's a more complex question, but it needs to be, the approach is, what is the best concept of safeguarding in respect for the machine, for safety, number one, and also, of course, on how to operate the machine. So it needs to be looked at from these criteria.
Okay, another person had a comment and a question. He says, it's the first time I've ever heard of the 2,000 millimeter per second approach speed. Is that new?
No, that is not new. Again, it comes out of the ISO 13855 standard. And also when you look at the NCB 1119 standard and the approach speed of the 1600 millimeters is there written in there. That is more common, but you will find comments within NCB 1119 that also says if your risk assessment calls out for a possibility of a higher approach speed, then you gotta use, the 2000 millimeters. So it really depends on your application. And standards are always minimum requirements. If you can do better, that's always a way to go.
Okay. Thank you. We have a lot of really good questions coming in. So this one is a little bit detailed, but let me go through it. Is there another way to measure stop time? I hear there is an automatic device that can be installed on the circuits to determine the stop time with higher accuracy than the video, especially for a robotic application. What do you think about that?
What I'm aware of, personally aware of, a specific device is for presses. There is a stop time performance monitor that can be installed or ordered with a press, because on a press you have a certain drift over time, and that stop time monitoring device will give you accurate measurements. So I know it from the aspect of presses.
Okay.
In regards of robots, I'm personally not aware of a device.
Okay, thanks.
But if it comes to stop time measurements, you look at the ANSI RIA 1508, the 2020 latest edition, and if it comes to protection of safeguarding with protective devices like a light curtain, and you look at the aspects that need to be taken there, and follow that standard.
Okay, thanks. This one might be a follow-up to a previous question. Have you used a meter to test light curtains? Is it based on 1600 or 2000 millimeter per second approach speed?
Again, it is based on that formula. Either you can use that in the NCB 1119 standard or the IEC 13855. If you have a finger, hand, arm movement, that's certainly quicker than a walk approach speed. So it is on the designer to determine, says, can I overcome a distance faster with my finger hand than with, for example, with walking towards it. That's the decision on the designer to make. So any time where you have to or can reach a hazard point, you got to be further away to make sure if you reach it, that it has stopped in time.
Okay, here's a different sort of a question. Is there anyone who has an app or a program that can help me do all the calculations if I provide the initial data?
Yes, you can certainly, contact, for example, manufacturer of these presence sensing devices. Also look into their manual. You can also give them a call, or companies provide, some software where you can, enter the data and see as a good estimation tool, where your safety distance is gonna end, or what the result is.
Okay. We're getting down towards the end of the question. So if people have a question that they would like to ask, at least ask live, go ahead and type it in now. If you have a question that comes to you at the very end of this presentation, we'll forward all the questions on to Thomas for his follow-up.
Yeah, more than happy to answer them. Yes. Mm-hmm.
So we do have one new question. How can I check if the current stop time for my manual lathe is okay when I open the interlock guard or I press the e-stop button?
Okay, so going back to that video method, now this takes a little bit more effort because when you open an interlock door, depending on that interlocked safety switch, does it have an LED, on it? Can you see a transition or not? In an e-stop, you see the button actuator depressed. But from there, you would go a little bit deeper and have actually the, if that video device or method might be to use is, you may have to have watching the, opening the door, and then you need to look at your control device status change on the LEDs on your control system. Or you go into the respective ANSI standards for the lathes, and that also gives you guidance in regards of the distance, because an OEM for these lathes, has to meet and be compliant with certain standards. And in the ANSI lathe standard, there is one. You can find that respective information.
Let us wrap up, unless we get one more question, but looks like this might be a good question to conclude on. Where can I get more information and more installation examples?
Okay, installation examples, and I mentioned that in the or touched in the presentation on that is, and within at least within recent years, I'm more and more impressed with operating manuals, from manufacturers for light curtains, for area scanners, and they give excellent examples on not just the usage, but also, of course, in relating to the safe distance. But always have in mind, reference the C-type machinery-specific type standards. That's the most important one. Be it domestically, an NCE Type B standard for a machine, or if you working on a CE marking project, you can use the European norms. So when I work on a consulting project, I need to get familiar, and obviously I know the type of machines machine that I need to look at. So I prep myself with the reference materials that get internationally, domestically, and also from OSHA. And those standards, you find information on the respective website and how to obtain them.
All right. Thank you, Thomas. Let's call to an end the Q&A session for now because we have reached nearly the end of the presentation. So let me, first of all, great big thank you to our speaker, Thomas Hertig.
Oh, thank you so much.
Just a tremendous presentation and a lot of great details. You could tell by the questions that came in. People had a lot of different specific questions. So you may be hearing more from them. And they're certainly encouraged to contact you directly.
Yes.
And also, thank you as well to our sponsor, Pills Automation Safety, for the webinar. And thank you to all of you in the audience for your attention and your great questions.
Right. Thank you so much.
On behalf of EHS Today, I'm Dave Blanchard. Stay safe and stay healthy. Take care.